For the info, it is 7:08 p.m. I would like to call this meeting of the Astronomy Club of Tulsa to order. Welcome, everybody. My name is Tamara Green. For those of you who don't know me yet, I am the president of the club. Let's see. Next.
James has got
next
James
slide,
has got
please.
the PowerPoint.
Does it show up correctly?
Yeah, it looks good.
Oh, are we recording? You can go ahead, Tamara.
Okay, next slide, please. I can't advance it. Okay. Welcome to the Astronomy Club of Tulsa. We're delighted to have you as members. As members, you will have many opportunities to join us in observing the beautiful night sky and make new friends and lasting memories for you and your families. Plus, there are many opportunities for public outreach to get others interested in our hobby. Also, please feel free to ask questions, offer suggestions, or volunteer to help out at our events. All new ideas are welcome, and we are glad you're here. Next. Upcoming events. Please note that due to the ongoing coronavirus pandemic, there will be no public or guest events scheduled until further notice. Daylight saving time ends on Sunday, November 1st. Members night and backup night will be Friday and Saturday. Members night, will be Friday, November 6th at the observatory. Backup night will be Saturday, November the 7th at the observatory. All times are to be announced, as apparently we're supposed to have some kind of discussion as to what time we actually want to start, because sunset is going to be early now. Members night is going to be on Friday, November 13th, with a backup night of Saturday, November 14th. Again, those are at the observatory. Thanksgiving Day is Thursday, November 26th. And unfortunately, due to the present health risks, there will not be an annual dinner meeting this year. We may plan on something for next spring if the pandemic is under control by then. Also, please observe guidelines that we have set forth for our observing nights. General meetings will be held via Zoom for the remainder of this year, and dates and times are to be announced. Next, please. We have guidelines for our observing nights. Set up your equipment at least 6 feet away from each other and remain at least 6 feet away from each other. We encourage the wearing of masks if you wish to chat with people, especially if we decide to open up the classroom in the winter months so that people can go inside and warm up. We especially want you to wear masks then. Please exercise proper hand washing and sanitizing. There will be soap and hand sanitizer in the bathroom. The classroom right now is only open for access to the bathroom. All other areas of off limits, and the dome is closed. But we may discuss the possibility of opening up the classroom so that members can go in and get warm when it's really cold. No sharing of equipment. There will be some club telescopes that members may use with designated eyepieces. These will be sanitized after each use. No children under the age of 12. All children must stay with their families at all times. And finally, relax, enjoy yourself, and have fun. Next, please. Okay, it looks like our new officers and board members are, I'm going to be your president again. Daniel Smith is going to be vice president. John Newton, treasurer. And congratulations to our new secretary, Richard Brady. Next, please. Welcome our 4 new board members, Adam Koloff, Brian Kyle, Don Bradford, and Jim Danforth. We're glad to have you all aboard. And returning board members, Michael Blaylock, Jerry Cassidy, John Land, James Taggart, and Skip Whitehurst. Thank you all for coming back. All right, next, please. All right, we've got 2021 astronomy calendars available for advanced orders, $10. Email John Newton at astrotulsa.trez@gmail.com. Those are really nice calendars. I buy one every year. They've got really nice pictures in them and all kinds of astronomical data that you'll find very interesting and fun. And it's a good price. And $10 for a calendar like that is good. Next. And don't forget about our private Facebook group, Astronomy Club of Tulsa members only. James, do you want to talk about this for a little bit?
Not much. We discussed about it last month, but just a reminder, everyone, we've got the group out there and we're starting to get a little bit of activity out there. So come join us.
Cool. All right. Next slide, please. And now the presentation, Understanding the Active Sun Through Satellite Observations, including the Parker Solar Probe and Solar Orbiter, presented by Dr. Aaron Coyner. Aaron, you've got the floor.
You can steal the share if you want.
Yeah, share my screen real quick. Okay. So I was kind of surprised when I got the email back that said you guys were going to actually allow me to do this, because I pop in every once in a while, but I was ever so curious with the number of people that are still in the club and still remember how much trouble I caused when I was younger, whether I would still actually be admitted to come do things. But I'm glad to be a part of today's meeting, and we'll do our best to make this as entertaining as possible. I make no promises, but we'll see what we can do. It is kind of a long title, Understanding the Active Sun Through Satellite Observations, including Parker Solar Probe and Solar Orbiter. Basically, it's that's my formal title, because if I didn't have a formal title, it would just be a clip from the Simpsons with Bart in Fall Out Boy costume going, "Watch out, radioactive man, the sun is exploding again." But here's how we look at the sun, and the sun is the central part of our solar system, of course, and you're dealing with the sun being very large to where side to side across the diameter, you could fit 109 Earths, which means the volume would hold 1.3 million Earths. There's no particular solid surface. It's all essentially a giant gas ball at various levels of compression. And we see a number of different layers, and then some of the layers underneath we don't actually get a chance to see because they are at least opaque to our optical abilities. But there is so much going on at the sun that we can't normally see under just typical solar observation. This is a video actually from Dr. Dusan Ostersil, who now works at George Mason. This was put together when he was at NASA Goddard, but it starts out with just kind of your average observation of the sun. That seemingly harmless yellow dot in the center is actually the sun. But as we pan closer to it, I'll start the video and you guys see it. As we pan closer to it, you start to see a little bit more activity. You see some of the coronal mass ejections coming off in the streamers. You see we're starting to zoom in. You see the ultraviolet, and then you see a flare going off with the actual X-rays. That's the white and the red. And then you're actually starting to see more of the flare. And then as you pan out from the flare, you see the larger coronal mass ejection that comes out of first the LASCO C2 camera and then the C3 camera. And then when it gets to the actual LASCO device, you see this snow of particles that are actually energetic electrons that are hitting the SOHO camera as a result of basically being directly in the line of fire of the CME that was Earth directed. And so as we look at all these things, a lot of, and I'm going to play this one more time so that we can talk a bit about it. You're looking at things in different wavelengths. So first you're getting kind of a visual aspect of the sun, and then in the coronagraphs, you're actually seeing white light imaging through Thomson scattering of electrons. Then as you get into the ultraviolet, you'll see the green, that's actually in the ultraviolet, and then you see the red and the white are in high energy X-rays. And the yellow is actually an extreme ultraviolet line as well. And so you're getting all kinds of information about the sun based on which wavelength you look at. It's similar to, you take a picture of any of us that are in this meeting, depending on what wavelength you look at, you get different pictures. If I take a picture in visible light, we look like we normally do. If I take a picture in sort of radio waves, I start to pick up heat signatures. And if I take a picture up in X-rays, I end up seeing essentially the bone structure, because the X-rays will penetrate all the way down through there, and then they'll reflect off the bone. So I see everybody in skeleton form. So depending on which wavelength you look at, you're getting more information about the sun. And as I said, there are multiple levels to the sun. There's the corona, which is always the really interesting part, because there's a lot of questions about the corona and how it behaves. It's the least dense of the layers of the sun, yet it is the hottest for various reasons. And it is also where a lot of the solar activity action happens, although most of it is driven, although the action happens in the corona, but it's driven by things that happen in the photosphere and slightly below. But you have the corona, you have what's called the chromosphere and the transition region. And then you have the photosphere, which is the visible surface. And then below that, you have a convection zone, you have a radiation zone, and you have the solar core, which is about 15 million degree plasma that is powering the nuclear furnace that keeps us all alive. And it's a good thing that we have a lot of different spacecraft that actually pay attention to the sun. It is the most observed object in all of astronomy, largely because of the fact that it has direct implications on life on Earth as we know it. If the sun were to decide to not be a giant furnace in the sky anymore, it'd be a very, very cold day for us in about 8 minutes. Luckily, that's not going to happen, but you can see among the list, this was from 2018. This is just the list of current probes that NASA has as part of their mission, either as NASA or with partners either at JAXA or at ESA, to look at and investigate aspects of the sun. We've got SOHO, which is the Solar and Heliospheric Observatory, which has been up for approximately, I believe, 27 years now. It's sort of the elder statesman. You have things like Stereo and SDO, which are more recent missions from the Stereo is in sort of the mid 2000s, and SDO launched in, I believe, 2010 or 2011. MMS and ACE, and those two actually take observations from the sun, but they're actually looking at some of the particles that get ejected outward. So those two are particularly particle sensitive, and they're looking at not only do we find the particle populations that get ejected from the sun into interplanetary space, but MMS then specifically looks at how they interact with the Earth's magnetic field. Hinode is another mission that launched sort of in the mid 2000s that does a lot of X-ray emission and also ultraviolet spectrometry on solar images. So it was an imaging spectrometer which allowed us to get information about temperature of flares and various other things at high spatial resolution. And we mentioned Parker Solar Probe up here, and Solar Orbiter is up there too, and we'll talk a little bit about it at the end of the talk because it's the most recent one. It was launched in February of this year. It's an ESA and NASA project designed to take the closest pictures on a steady stream basis of the sun as it's going to reach a Lagrange point roughly 42 million miles away from the surface, or about 3/4 of the way from Earth to the sun is where it will park, and then it will take observations. So why do we care? Well, when we look at different wavelengths, in this case, the one in the middle is sort of a combination image from AIA, which is the white light coronagraph from SOHO, and it's also got a extreme ultraviolet AIA filter image, so you can get different pictures of where the activity is. You can sort of tie the helmet streamers that you see in the coronagraph to active regions on the solar surface. The composite image from the white light and the H alpha, you start to see where the plage and the different sunspots are actually located. And if you're looking at things at say 4500, this is more of a photospheric observation. You're seeing a typical photosphere, kind of a white yellow ball, and you've got the dark spots that are the active sun due to the sunspots. But when you're dealing with observations of solar activity, you start to look at it in a number of different channels. And this is from SDO, where you have the two different things. You're looking at the HMI Dopplergram and the magnetogram. That tells us a lot of information about the magnetic field in sort of three-dimensional space coming off of the sun. So we're looking at not only north, south, and east, west on the plane, but we're also looking at toward us or away from us in terms of a three-dimensional component. And it's the structure of the magnetic field that often tells us more about the activity that is ongoing. And we'll talk about that a little later when I get into some of the more elaborate constructions. You've got a continuum image, which gives you the sort of the visual light picture. You've got the 1700 angstrom image along with the 1600 angstrom image, which shows you essentially the chromosphere and the transition region between the photosphere and the chromosphere. That sort of gives you kind of the base of where the solar activity starts to appear. And then we get into the corona, and you're looking at AIA 304. That's actually a helium line. So we're able to essentially trace helium in the atmosphere, and it actually gives us an idea of where the solar activity is based on the presence of helium. AIA 171, 193, and 211 are all different iron lines, and they all represent different temperatures. 171 is about 600,000 degrees. 193 is about 1 million degrees. 211 is about 2 million degrees. There's 335, which is really good for active regions, which is about 2.5 million degrees. This is where active regions and flares typically start. You tend to pick up more emission in these higher, different wavelengths at different temperatures. And the higher temperatures, you tend to pick up more emission from the flaring regions than from, say, a quiet sun area. So 335 is particularly beneficial when we know that there's an active region or potentially a flare or a CME. 94 is another extreme ultraviolet. It's starting to get toward the edge of the ultraviolet and starting to work its way up toward X-rays. It's looking at a region that's about 6 million degrees. So these are particularly strong during flaring regions or flaring active regions. And then 131 is an iron line that actually only responds at temperatures of about 10 million degrees. So this is typically seen during the middle of flares. We'll see plasmas get excited to that temperature. So we can use all of these different wavelengths to sort of construct what does the sun look like and how is the sun behaving on any given day. And why do we care? Well, when you look at the sun, it has a distinct solar cycle. It's about every 22 years, or there's 2 cycles every 22 years because of magnetic pole reversals. The sun's magnetic poles reverse about every 11 years. So one cycle will be the poles reversing one way, and then the follow-up cycle will be the poles reversing back to the way they were 2 cycles ago. And within these cycles, there's about an 11-year stretch, and about 5 to 6 years into a cycle, we get to what's called solar maximum. And that's where we find a lot of solar activity in terms of flares, in terms of CMEs, in terms of active space weather that is being sent towards Earth and throughout the interplanetary space that is the heliosphere. We happen to be most concerned with that which is Earth directed for obvious reasons. We're a little bit selfish in that regard, but it does tend to shoot high energy plasma at out of all points of the heliosphere. So even on Mars or on Jupiter, we do see interactions with the solar wind and with solar energetic particles from flares that interact with the various magnetic fields. And this is a textbook figure from the astronomy textbook that I used from OpenStax, but this is an example of what we see in terms of a cycle. So we'll start out at essentially solar minimum. We have essentially a poloidal field that will just start out as essentially a dipole with the magnetic north pointing up, magnetic south pointing downward. We've got the field going that way. And then as time progresses towards solar maximum, because the sun is not a solid ball, different latitudes of the sun rotate at different speeds. And the equator of the sun actually rotates faster than the poles do. So these magnetic field lines that are embedded within the sun and within the solar plasma get stretched and they get twisted. And so due to what's called differential rotation, you get basically a distortion in the field that arranges the field by the time it gets to solar maximum to where the field is almost what's called toroidal, where it creates a very strong field at essentially low latitudes toward the equator. And the strongest field is actually within about 30 degrees north to 30 degrees south of the equator. And that's where we start to see a lot of the sunspots that develop during solar maximum, as we see it kind of in those mid latitudes to low latitudes approaching the equator. And then as time continues to stretch these out for the other half of the cycle, they essentially stretch out, and by the end of the cycle, they've completely been flipped around. And then we start over again with the next cycle that will flip them back to the other way. This is a simple cartoon. Ideally, this is a very idealized cartoon because we don't like to draw things as complex as they actually are. If we had to have this in full pictures with a lot of video, it would get far more complicated and complex than this particular structure allows. But you can kind of see where the field starts to distort. And the distortion of the field over the course of the years leads to the sunspot diagram that we refer to as the butterfly diagram, because we astronomers and astrophysicists are not particularly creative with our naming. You can see that for each cycle or pair of cycles, you actually see diagrams that essentially start to resemble a butterfly. And as we continue to move out, you're starting to see more and more sunspots, but they're all essentially between 30 degrees north and 30 degrees south, with the equator running through the center. You don't see much in the way of, in in the way of activity above 30 degrees north or below 30 degrees south, you do see sporadically, you'll see a active region, but we don't see as much toward the, you don't see as much toward the poles as you do toward the equator. And that has to do with, again, that twisting of the magnetic field that happens toward the middle of the solar cycle towards solar max. So in terms of solar activity, what kinds of things do we want to look for? Well, we want to talk about solar flares and we want to talk about coronal mass ejections. And the reason we want to do that is because those types of activities actually lead to energetic particles, electrons, protons, helium nuclei, nuclei of heavier elements that get essentially shot out into the solar wind, and often actually shock accelerated to where they're moving much faster than the typical solar wind and headed along the Parker spiral until they interact with a magnetic field, which could in fact be us, or it could be Mars, or it could be Jupiter. And when it interacts with our magnetic field, it creates all kinds of fun things with space weather. A lot of we, the amateur astronomy community, generally like to hear about aurora sightings at various latitudes. And if you get a strong enough flare or a CME, I know I've had it happen a couple of times when I used to live here, that there were a couple of days that you could actually see the aurora almost as far south as Tulsa. It took a significant solar storm to be able to do that. Where I live now, it's a little easier to go find a place that you can see the aurora from, except where I actually live on the coast, it typically ends up being cloudy and it's not particularly conducive to amateur astronomy, but that's why occasionally you go make a trip onto the other side of the Cascade Mountains, and then it's a little better seeing conditions because you're not dealing with the rain all the time. So why are we concerned about these? And this is a video. This is an example from AIA 211. This is a flare from 2018. If I can get it to start. There we go. And it's just a video that's going to go, and you'll see these larger bands of basically active regions. And you see these things called coronal holes, these dark regions that are actually regions that are easy for particles to escape from. So if you have an active region next to a coronal hole, it basically means that you have access for those energetic particles created by the flare or created by the CME to escape into interplanetary space. The reason the coronal holes are darker is essentially it's a reduction in density. So the darker regions of the coronal hole, there's actually less plasma there. So it's easier for the plasma to escape into that direction than trying to slog through all the dense plasma that is the active region. So it ran that once now. So when we talk about, oops, there's one. This is a video from NASA Goddard, and actually sort of not going to adjust my sharing, but I am going to get this to where it'll actually play the video so you can hear part of it. And we're still sharing the PowerPoint. And so this is a video from NASA Goddard. They have a better budget than I do, so they put together cooler videos than I can. This is a prominence, which is the same thing as a filament on the solar surface, but you can actually see it sort of escaping off the limb, and you get this nice ring prominence. The Earth is there as an image to scale, just to give you an idea of how gigantic these things are. We play the video. I won't play the entire video because it's 4 minutes long, but let me. has to go and proceed to this level of precision. But you start to see all these loops. These are actually magnetic structures that are highlighted by plasma that is trapped in that magnetic field. Particles that are going down from the top where what's called the reconnection export happened, and then the particles are coming down to the actual surface. You can see those points in the actual flow. And so a little bit like it comes off of that. And I'll stop it for now. It's okay. So essentially what this does, this actually creates a loop that you can get to our, creates a series of loops that create a structure called a post-flare arcade that originally starts with the energetic X point that is at the top of the flare loop. And then as the particles start to train down to the actual surface, you get an intense brightening and a larger amount of emission that comes out of this. Now, that's a flare itself, but then as you look beyond the flare to what else can happen, we have cartoons for these things. And you have basically a flare that can create, what happens is particles are not supposed to cross magnetic field lines. But as your differentially rotating hot ball of gas with a magnetic field in it is differentially rotating, what happens is it starts to twist up the magnetic field lines, and eventually oppositely directed field get going close enough to one another that particles can diffuse across just by essentially diffusion limitations from essentially quantum mechanics and Heisenberg uncertainty. There's only there's only a certain level of accuracy that we can know the position of a particular the position of a particular electron or heavy element or anything of that sort. And if they actually get to where they can cross between oppositely directed magnetic field, you actually create current sheets in the atmosphere that essentially equate to having a short circuit, where a large amount of electrons or a large current can flow very quickly without there being much resistance to the flow. And what happens when you have one of these is if you have a reconnection site sort of in the middle, you have a bottom half that actually acts as a flare and has escaping particles that are going to train down to the foot points of the flare, and that part you'll actually see as the flare on the surface. The top part above the reconnection site blows off into space and becomes a coronal mass ejection. And just so that we acknowledge that this is not that this is a cartoon, but just so that we don't think that we just made the cartoon up, there's actually a good video example of this. Where we can see things start to build up, and there's the reconnection site. You start to see the reconnection site, and you see some of the other stuff above the reconnection site that breaks off and gets sent off into space. There's our primary reconnection afterwards, and there's our post loops that come in, and we still have some X-rays. That was the green that are up at this loop top source after that top half has blown off. I'll let it run again so you can see it. We have a reconnection piece here that blows that off into space. and then the rest of the reconnection happens and creates the post loop. So this is some work that I did when I was in graduate school from a flare that was from 2005. And this was a paper that I got published in 2009, about 10.5 years ago. When we see flare structures in the ultraviolet in the chromosphere, we don't necessarily always see these perfect loop structures. We see a lot of loop structures, but we also see some that are sort of three-dimensional conglomerates of a lot of loops with a very large sort of expansion rate in 3 different dimensions. And if we pair that, the ultraviolet, which is the background, to where the X-ray signatures are, they don't necessarily always match up to where we think we can see them. Here you see source 1, which is down, which is actually up at the top, which is UV source 1, which is that top corner. And then there's UV source 2, which is the bottom portion of this whole thing. And we're comparing sort of our ultraviolet curve to the 50 to 100 keV X-rays, which are the white circular overlays on the smaller image, that don't necessarily correspond spatially to either box. But we see that source 1 and source 2, the 2 endpoints of the ultraviolet, are still fairly well correlated in time to the emission that we're seeing in the X-rays, even though if I look at the spatial distribution of the X-rays, there aren't as many X-rays in the 2 endpoint boxes. There are some toward the middle where we actually see some in source 1, but we don't see as many in source 2. And early in the flare, we don't actually see any in the lower source. And by the end of the flare, we're not seeing any in either place, but we're still seeing some actual emission that shows up. And this indicates that the X-rays are occurring at the loop top structures, but these loop top structures are actually having essentially tendrils that are going further out into space and creating more of a 3-dimensional setup than just a single loop. And so when we talk about 3-dimensional reconnection, we're talking about connecting a separator box to where each one of these separators is essentially a source that creates sort of a 3D bubble of different aspects that can be connected to different foot points on the surface that create the ultraviolet emission that we see, but we can connect any of those foot points to any point on the top of this separator bubble that could create the X-rays. So we end up with a much wider potential field of X-ray emission connected to ultraviolet emission. And that's the only bit of self-aggrandizement I get to do, because that's the one piece of my actual work that's in this talk. The rest of it is observations from various satellites and presentations from friends and colleagues of mine. We're going to talk a little bit about coronal mass ejections, which is the other part of solar activity that has the most impact on our space weather. Coronal mass ejection is exactly what it says it is. It's where we take mass from the corona and we throw it out into space. And so here you see a number of cases of CMEs looking through the LASCO coronagraph cameras. You can see sort of the CMEs develop and they expand outward. This is one where, again, we have a NASA video where SDO observed an actual CME forming. I'm going to trick this one by not actually playing the sound, but we can see some of the video as we do So there's our solar system. And this is why we're worried, because these energetic particles blast in and they affect our magnetic field. And they're due to strong magnetic fields within the sun. And these are all models, and we expect to see them in terms of sort of CME initiations like the one you see there. But recent observations from SDO actually showed this process coming to be, looking at the flare and the CME that came off that edge. You can see kind of the flare come up, and then you see the CME blast off. And this has to do with the magnetic field in the core. I'll skip through a little bit of this because it's. And so we have two active regions at both ends of this. We have a connection between the two active regions that creates this. This is the SDO spacecraft. And then it's looking through the various filters. And here it's looking at 211. And we see a flare developing in the lower portion of the sun. We see a flare develop, and then we see a very quick develop of a large flare that turns into a CME. And looking from LASCO, we can see the CME shoot off. And it's right here where we have, there goes the CME as it develops. You watch it form the flux rope, and then it reconnects at the bottom. In these figure 8 patterns. And then once it reconnects, these figure 8 things get launched into CMEs at the top. So let's see. All right, so when we talk about CMEs, there are 3 basic parts of the CME. There's the leading edge, which is the part that explodes from the original reconnection event. Then there's a bit of a cavity because there's a bit of a delay before the rest of the CME gets projected outward into space as part of the core. So whenever we see a CME, we actually do see these sort of front edge shocks. Then we see kind of a cavity behind the shock, and then we see the larger core progress. This leading edge is actually going to shock accelerate most of the plasma in the solar wind, and actually leads to things like our geomagnetic storms that allow us to see the aurora. Potentially, depending on the strength of it, if it can penetrate to a ground level event, it's one of these events that tends to lead to some of the blackouts that we've heard about in various astronomy meetings or astronomy classes due to the interaction of energetic particles with the power grid. Satellites are typically in danger of having things bit flip because they'll interact with energetic particles, and it'll cause a interaction with the circuit board and cause them to turn on or turn off when they're not supposed to. So there are lots of reasons we pay attention to these CMEs, but it's largely the CMEs that create and drive most of the space weather events. So again, why do we care about space weather? Well, some of us like to see pretty lights like the aurora. Others of us like to actually communicate with people, either via normal communications or satellite communications. And we do tend to send people into space, or at least we did for a while, and now we're getting back to it. And a lot of us like to fly on aircraft. And all of these different systems can all be affected by space weather to the point where we have to be concerned about it and at least monitor it. And NOAA has a very good site for doing that. They actually have a space weather prediction center that actually gives you a better idea of what the space weather forecast looks like for a given day. Like any weather forecasting, it is in part a guess, but it's based on computer models. To the best of my knowledge, the space weather forecast is slightly more predictable, is slightly better than trying to predict the terrestrial weather here in Oklahoma, which we freely acknowledge is is a random guess at any given point. So among the, we talked about how we do the observations and what kinds of things we look at. We want to look at kind of what questions are there to still answer. One of them is coronal heating. I told you the corona is the least dense, region of the sun, but it's also the hottest. And it's also the furthest away from the core. So the fact that the hottest layer of the atmosphere, but it's also the furthest away from the core, which by typical heat transfer doesn't make a whole lot of sense. But we don't know necessarily why it's as hot as it is, but we actually have seen through SDO some things called spicules and microflares that actually start to increase the amount of X-ray emission and the amount of high energy material that gets into the corona. And when we look at Parker, we're looking at how does the solar wind influence these? We talk about SEPs, which are solar energetic particles. These are highly energetic electrons, protons, and heavy elements. They're accelerated from space, from essentially solar events like flares and CMEs. They tend to impact communications. They cause difficulty with astronaut health, and they can affect the power grid for large events. And they've all been measured remotely in situ at Earth, but what happens in between launch from the sun and when we can actually measure them at Earth's atmosphere are still questions that we're not entirely sure of. So we have some missions that are currently up and some future missions that'll address that. This is one of my favorite artist renditions. It's essentially the sun. It launches things at us, and we of course have our magnetic field, which is our shield to get through it all. And it's the interactions within the magnetic field that cause all of the fun things that we actually see on Earth. This is an artist rendition of MMS, which is a series of 4 satellites that travel in and out of the Earth's magnetic field, looking for signs of magnetic reconnection on the day side or the night side as a result of interaction with solar particles. And of course, we can't have a space weather talk or a solar talk without having at least one. And this is from astrophotographer JC Casado. We have to have at least one decent aurora photo per solar talk. It's a requirement. Now, I actually want to sort of turn today's talk into talking about the current missions that we have, and these slides are actually from a colleague of mine at Johns Hopkins Applied Physics Lab about Parker Solar Probe. And this is our Living with a Star, the NASA program that monitors solar missions and actually proposes them is called Living with a Star. And the reason Living with a Star exists is because we see things like the Northeast blackout from 1989 and any number of aurora events that are all tied to solar events, and we need to learn more about how the sun behaves so we know how best to behave around its little temper tantrums. And so Parker Solar Probe was a mission that was designed to fly as close as possible to the sun without melting the spacecraft. And if we were to compare it to a football field and we're sitting on the opposite goal line, by the end of its closest approach to the sun, Parker will sit at about the 3.5 yard line of opponent territory. So we're about 97% of the way to the sun when we're dealing with Parker Solar Probe at the end. And this is sort of the timeline as it goes on. Its mission is supposed to continue until 2024, and it will continue doing these passes until about 2024 when it gets close enough that I think it'll overheat. The green orbiter here is actually solar orbiter, and it's getting into position, but when it gets into position later on, it gets closer to there. So we launch Parker essentially at solar minimum. By the time we get to the end of Parker's mission, we should be observing it at solar maximum. So we should be closest to the sun during solar mission, and that would actually allow for better understanding of what these energetic particles look like as they're leaving the sun and before they get to Earth, among other things. So in terms of early results during those first couple of passes, we actually discovered some areas that are called magnetic islands. These have been simulated in numerical simulation for years, where we'll get clumps of essentially magnetic topology that will allow for particle energization and heating. So these are small areas of intense heating that would then dissipate through the rest of space, but you end up with essentially hotspots within the corona itself due to these magnetic islands. We hadn't seen these in space or in our previous observations because we hadn't seen them at the level of detail that Parker was capable of. But with our WHISPER instrument, we're actually able to detect some evidence that the magnetic islands exist, at least on the first pass through by Parker, which was last year. And we can actually see these because if we look at this is an image from WHISPER, and you can see where essentially where the red dots are located. You can see kind of the green outline. This is actually a magnetic outline or a magnetic island, and the intensity and the temperature is actually going up around this island compared to the rest of the neighboring images. Henry Norris Russell predicted in 1929 that there should be a dust-free region around the sun, close in, where basically all the dust gets eradicated by the intense radiation. But we hadn't actually been able to see that yet. But with WHISPER, we also have from last year, from 2019, we have evidence that the dust-free zone actually exists. From our ISIS instruments, there are energetic particle events that occur during quiet sun conditions, which are much weaker energetic particle events, but they still can occur during quiet sun, which is essentially during solar minimum, where there aren't as many flares or CMEs. So we get some small scale events. I'm not going to pretend to be able to fully explain this talk, but essentially what we do see is we see some peaks in solar energetic activity, even during quiet sun conditions where we're not seeing any flares or CMEs associated with it. And when we look at the magnetic fields through the fields instrument and also the sweep particle analyzer, we actually see magnetic switchbacks in the young solar wind that actually lead to the possibility of energetic particles being instrumental in some of the coronal heating aspects. This is from Justin Casper, and this is an example as it's coming out. You'll notice as the solar wind is coming out, you actually see these curves that look like switchbacks, where it starts to go up and then comes back and then goes back up again. When those energetic particles come back into the corona, they're actually going to deposit energy a little bit in the corona, which actually allows for additional coronal heating within the early stages of the solar wind. And we see these things in looking at the magnetic field, and in looking at the magnetic field strength, we can actually see these types of switchbacks that we observe. So this is another project that's a colleague of mine, Craig DeForest, and an entire team. They actually, some of the team works at Goddard, some of the team works from Sweary and Boulder, some of them are from the Naval Research Lab. It's an instrument called PUNCH, which is supposed to launch in 2023, that is looking at the corona and the solar wind essentially as a single system. And so when we look at solar physics and observing things, it's actually two separate fields. There's the solar physics, which looks at, okay, what do things look like at the sun? There's heliospheric physics, which is what does the solar wind and basically the interplanetary plasma do as a result of the things that happen at the sun. And so we have observations at the sun. We have observations that we make at Earth and at other locations in situ, either via satellites in Earth's atmosphere or satellites that we have out in space at different locations. But there isn't really much that we know from the time it leaves the sun to the time that we get our in situ measurements. And PUNCH as an instrument in 2023 is designed to sort of look in that gap in between and sort of try to explain what happens to those energetic particles from the time they leave the sun to the time they're actually measured on Earth. What can we learn about their travel along the way? And so the science driver for PUNCH is to actually understand how the corona gives rise to the heliosphere and the solar wind. And we do direct continuous 3D imaging in order of the entire outer corona and inner heliosphere using polarized Thomson scattered light every 4 minutes while the different satellites are up there. It's 4 synchronous small satellites in low Earth orbit at 570 kilometers. And it has a 2-year duration and it's slated to launch in early 2023. They're currently working on their design, and it's still slated for launch in 2023. Last I spoke to Craig. We shall see if that mission timeline still continues, because I know a lot of the other missions that are scheduled to go before it are being slightly delayed due to the coronavirus pandemic. So what we're looking for is we want to look at the ambient solar wind. We want to know how the corona structure becomes the ambient solar wind that we actually find. Are there 3D dynamics with shocks and different shock morphologies? Are there rotation regions? Is it sort of a global evolving solar wind flow, or are there CME trajectories that come into play? All of these things we actually need to investigate in more detail than we have been able to previously due to limitations in technology. And then the current mission that has done the most recently that has been launched, this was actually launched in February and had first light images in July, is the Solar Orbiter, which is a joint project, a joint venture between the European Space Agency and NASA. And as it gets closer to its final orbit, it gives you the closest full disk solar observations and solar images of solar activity and solar wind structure. But another key thing about Solar Orbiter is the orientation of its orbit actually makes it travel around the poles of the sun. So whereas things like SOHO and SDO and Hinode and the other satellites typically gave you the most high resolution imaging of the equator, Solar Orbiter is designed to focus a lot on the polar regions, because we don't know as much about what happens in the polar regions as we do about some of the equatorial stuff. And this is just a combination of some of the first images and the first findings. This is from ESA and NASA. This is a first light image from July of this year. The results got published in August. And within these images, if you look at the little small bright spots, these are things that are referred to in the Solar Orbiter by the Solar Orbiter team as campfires, because they're little micro scale flares. They're solar flare activity, but they're on micro scales compared to the typical scales of the larger flares that we see. But these micro scale activities that we wouldn't be able to see with our previous technology may be putting in enough energetic particles in, and I'll zoom in on sort of the campfires on the sun, and there's a little bit of a video with this, but there's no audio with this video. It just shows kind of the video as it evolves, and you see these smaller specks that are sort of these campfires, and we believe these sort of micro flare events may be essential to creating the causes for why the corona is so much hotter than the other levels of the atmosphere, because they're depositing more solar energetic particles in the corona than beforehand. And just as my last slide, I do want to thank Dr. Narafai and Alita Higginson from Johns Hopkins Applied Physics Lab, Dr. Nikki Vile-Kepko from Goddard, and Craig DeForest from Southwest Research Institute Boulder. Some of the images are actually from my astronomy textbook, which was by Andrew Fracknoy. And the reason I'm able to do these sorts of talks, aside from my background in solar physics, is I'm actually part of the NASA Solar System Ambassador Program that's run through JPL and Caltech, where I'm a volunteer outreach presenter for clubs like yours at the Astronomy Club of Tulsa and schools and libraries around my local area. And the Solar System Ambassador Program allows me to do the things that I do. And with that, I will take a breath. I'll allow you guys to ask whatever questions you may have. It may take me a couple of minutes to respond because I need to catch my oxygen, but I will take a break there and we can do questions if anybody wants to.
Very good, thank you.
Yes, thank you, Aaron.
No problem.
Yes, thank you, Aaron. It was a great program. It's good to see you again.
Good to be here. It has been a while, but I figure I should show up every once in a while just to cause trouble.
Can you share a little bit about what you're doing out there in Oregon?
Right now, out in Oregon, I am the associate professor of physics at Southwestern Oregon Community College. I single-handedly run the physics and engineering programs. I am currently also the faculty member that is in charge of the Invent Oregon program in terms of our contribution at Southwestern Oregon Community College. It's a student inventor group and a student inventor competition that is run through 20 different colleges and universities in Oregon, where groups of student inventors are encouraged to develop a tangible product and a tangible prototype. And they have basically 6 months to do it. And then at the end of the state finals, there are competitions where the student teams can get up to $25,000 to $30,000 to help with prototyping and help with marketing of future products as they go along. So we have a program called Inventor that actually teaches the students to think sort of not only as an invention from a scientific perspective, but also looking at inventions in terms of products and in terms of marketing. We are involved in the NASA Oregon Space Grant Consortium, which allows students of mine to actually continue on with NASA research similar to what I did in my undergraduate and graduate career. Allows students to get involved with NASA related and NASA funded projects. I have sent, some of my students have gone for little week-long programs to various NASA centers. So we keep students busy, and we keep giving them opportunities to not only do their typical first 2 years of their college experience, but also get opportunities to get involved in cutting edge research, which is one thing that I'm very proud of, and one thing that I always look forward to getting students involved in. And then outside of the school, I am, because of the Solar System Ambassador Program, I am always actively promoting space science and space education by doing talks like these. And I'll talk to libraries, community events, elementary schools, middle schools, high schools. And we do our best to keep everything, to try to keep science and space education and astronomy in the forefront for our community locally, as well as anyone that we can reach virtually through our various social media platforms.
The inventor program, is that secondary or college or both?
It is a college level program, although they are branching out to where I think eventually they're going to start incorporating some of the high school level students as well. But for the time being, it's a community college and university level program.
Can you give us any prognosis of solar cycle 25? That seems to be sputtering along.
I think it seems to be sputtering along a little bit, but I haven't seen any updated projections, at least recently. But I think they've officially come to the realization that, or at least according to what I read last time, that supposedly November, December of 2020 was like the official, or November, December of 2019 was like the official solar minimum. And we're actually starting to work our way back up, although we're just basically less than a year out of solar minimum. So we're not seeing as much activity, but it's very similar to when last cycle started. I had just moved to NASA Goddard and was working in the solar physics building, and we had a slow start to last cycle, enough to where a lot of the scientists that I was working with were frantically writing proposals to try to get funding to explain why this particular solar minimum was taking so long to get out of, so that they could continue to get funding for things, because we had a stretch of like 100 days where we had no sunspots. And when you're in a building that focuses only on solar observation and solar science, and there's no activity to really observe, people get a little concerned about things. I saw a question in the chat from Robin Jones, and I will address it. As a few of you know that are still here, and that's why I'm actually surprised I got invited back. I was a member of this very organization for a fairly long time during my high school and early college career, and I'd actually made a few guest appearances when I was a small child, but I wasn't officially part of the organization until I think my junior or senior year of high school, and then the entire time I was at TU as an undergrad. And I was heavily involved in the club, and in 2003, when we decided to host the Mid-States Regional Astronomical League Convention, I was rather involved in putting that convention together. And in a sense, the reason I was involved in the club is a lot of the same reason why I'm involved in the space science research aspect. I was always sort of driven to be a space cadet. It was just always one of my things that always connected with me. And so having an opportunity to learn from people at the astronomy club and get to experience more things involving astronomy, involving solar observations, involving space observations of all kinds have kind of led me sort of along the path that I'm on now. And it also brings me back to the, not only am I in the research path because of my experiences in astronomy early on, but I also look at my role as an outreach ambassador coming back and giving these types of talks as sort of my due diligence and sort of paying back those that mentored me as I was going through the system and going into sort of my career path. So yes, those of you that are at the club, we encourage you to continue to explore the night sky and continue to bring people along with you. And that's always been my hope as far as the things that I do. Other questions, comments?
I've got one actually. I've got two questions.
Right.
My first one was, is there like a speed record for how long it takes for particles from solar wind to travel from the sun to the Earth?
Typically, I think the fastest we've seen, the fastest ones we've seen typically travel at about 3,000 to 4,000 kilometers a second. So they will typically travel. I think the fastest we've seen a geomagnetic storm off of a solar event that we could track was something on the order of between 12 and 15 hours after the solar event happened.
Wow.
The energetic particles had hit the Earth's atmosphere. Typically it's 2 or 3 days, but the faster ones the bigger ones can tend to be a little faster.
It's a shame we can't use that to get around. That would be pretty handy.
It would be.
Yeah. Now, my other question was about something I actually just learned last night. I was watching a documentary about Skylab, and it mentioned that I guess sort of the sort of nail in the coffin of Skylab was that there was solar activity that affected our atmosphere in such a way that slowed it down to deorbit it. Is that true, or is that just something they made up?
From what I understand, and admittedly, my knowledge of this comes from a similar documentary to the one that you watched, but I believe that is actually part of the reason. I'm not sure it's the primary reason, but there was a little additional interactions with the energetic particles coming into the atmosphere that were causing essentially additional heating and thus additional friction within the atmosphere that was actually slowing the satellite down slightly.
So they were pretty vague. They just wanted to talk about how it burned up in the atmosphere real fast, and so they just threw that out there. I thought, wait a second, I didn't know that. So that's kind of sobering to think that the sun can down a space station.
Well, as a senior citizen, the Skylab in its last 1 or 2 orbits actually went over Tulsa.
Oh God.
And there was some possibility in big news story that, we might get to see it. Ended up crashing into Australia, I believe. But, we had the solar maximum was near. And as Aaron, Dr. Corner said, that heating caused the Earth's atmosphere to expand and caused, extra drag on the spacecraft. And back then, they didn't have the ways to alter the orbit like we do with the space station. Now they didn't have the thrusters and things. It was just kind of a passive orbiter. So it eventually came down on somebody's sheep farm on the
Yep.
coast of Australia, I believe.
I was always told that the fatality of the Skylab impact was exactly 1 cow.
1 cow.
We have a little tiny piece of Skylab in the planetarium, but I think most of it is actually still in Australia. Apparently they built a museum where it landed, and they have like a couple of its oxygen tanks and a few other odds and ends that are fairly big.
Yeah, we had some Oklahoma astronauts on it.
Yep.
Pogue, I believe his name
Yep.
was, from Okemah area.
We had Bill Pogue and Owen Garriott were both from Oklahoma.
Yeah.
So another question from the chat: what challenges or opportunities do you see with regard to bringing young people into astronomy? I think the biggest challenge that I'm seeing, but the biggest challenge I'm seeing is also the biggest opportunity we have. One of the biggest challenges I have with young people is the sort of instant gratification culture that we're in, that getting them to actually pay attention to things long enough to know that these are sort of important, and then actually spend the time to go make the observations when typically they're looking at either their phones or their devices, or looking for some level of technology to tell them that this is a very interesting object, and then they'll go outside and they'll pretend like they actually cared for a minute, and then they'll come back in. But what I have noticed in the teaching opportunities that I do is that astronomy and space sciences are still unique in the sense that they provide sort of a gateway science to the investigation of other sciences. I have a lot of students that will happily take an astronomy class where if I ask them if they want to take one of my physics classes, they cower in fear and then leave. But if I can get them into my astronomy class, and they start to realize that all the cool stuff that they've heard about in astronomy is actually governed by all the laws of physics, or when we start talking about the spectral analysis stuff, we start talking about more chemistry stuff. Yes, I will include chemistry in there, Miss Angela, because that does happen. And we can use sort of astronomy as sort of a nice lens to branch out into other sciences where students would not necessarily track into a chemistry lab or track into a physics lab without some initial exposure to astronomy, essentially as sort of a gateway science. So I hope that answers your question, Robin.
When I was in high school in New Jersey, I got to see the aurora borealis. In fact, I looked it up because kids kept diaries back in those days. It was March 1969. I just did a quick Safari search on my phone. I came up with a newspaper article describing it. Is there a way, if you look back in history, to see what an aurora event was? Because to see it in New Jersey is a little bit on the uncommon side. Is there a way to go back and figure out what was going on at that time?
I'm sure there is a way to do that, and I'm sure there are archives of data to that extent. I will go back and I will talk to a couple of friends of mine that actually work at the Space Weather Center and see if they know anything about archives for those, and I will send that information to John Land, and I'll have him send, if there is an archive available, I'll have him send it out in the next newsletter.
Oh, so that would be awesome. Thank you so much.
Seems like I remember the late 1950s was a very high peak of solar activity. So.
I think that was one of the peaks of one of the stronger solar cycles, although I have only the record books to go by.
Well, here's what I wrote down. March 23rd, 1969. There were red patches and streaks, white and green streaks and arcs. That was from somebody who really didn't know anything.
69?
This was March 23rd, 1969. I think it was broadcast on the radio or something, because it wasn't anything announced in advance. So we all went outside, it was around 10 o'clock at night or so, and looked. and it was right at the zenith. It was beautiful. And another time, I was heading back to London where my family lived at the time when I was going to college. This is around Christmas time. TWA 747 crossing the North Atlantic. Pilot gets on the plane and says, okay, if you look at the left-hand side of the plane, you can see the green curtain northern lights. 2 people on the entire plane bother to get up and look. I was shocked.
I always get kind of surprised when you're presented with opportunities like that, that not more people take advantage of it. But that's what we come in, is we're supposed to try to instill that amount of wonder into generations as they come in, to encourage them to keep looking upward and looking outward into space.
I mean, granted, if you live in Tromsø in Norway, you're going to see them all the time. But if you live, in this part of the country, you're not going to see them that often. And to be presented an opportunity on an aircraft and then not bother to take advantage of that, that's ridiculous. I can't imagine that.
Hey, you'd be surprised if people on the plane didn't even realize what it was they were being told to look at.
True.
Yeah.
Would have been easier to just say pretty green lights that way. Then they'd look.
Well, actually, he didn't say green curtain. He just said northern lights, but they were the green curtain kind. But yeah, he just said northern lights on the left-hand side of the plane, and two people, I think, on the whole plane got up to look.
2 very bright people.
So this was another quick question from Robin in the chat, asking what my favorite deep sky object is. Yes, I spend most of my time at work looking at solar objects, but when I get a chance to do astronomy stuff, my favorite object is actually Messier 104, the Sombrero Galaxy.
That's a good one.
As one of my favorite ones. That's typically the background on my computer at work, and alternates at times. My background on my laptop is that one. Sometimes I have different ones. Like, since I did one of the things that myself and Crystal Hopper, my best friend and collaborator that works with me in the physics and astronomy department, or physics and engineering department at SWAC, we had put together a exhibit for the 30th anniversary of the Hubble Space Telescope. So there's a lot of random things at work that have, like, the bubble nebula and some of the other rather cool Hubble pictures as sort of backgrounds on the various computers that we have access to.
How long are you going to be in the Tulsa area?
I guess that kind of depends on the weather, but technically I'm supposed to leave Wednesday morning, but I guess it depends on whether the airlines will actually let me fly out based on what the weather decides to do.
Hope you're not flying through Denver.
No, I'm not going through Denver. I'm actually going through Houston and then going back up that way, because I have a sister that lives down in Houston. So when I have an extended layover, I'm going to try to spend some time down there. Although I heard from watching the news today that I guess they're bracing on the Gulf Coast for another hurricane to go through. So hopefully I can manage not to time that one right.
Hey, at least it's just weather. Usually every time I go on vacation to somewhere where there's a volcano, it goes off a month later. So I went to Yellowstone 2 weeks ago, so I'm real nervous right now.
I can understand that. Yeah. Once again, I do apologize, because every time I come home after being gone for a while, the weather decides to go haywire as soon as I show up. So I will take personal blame for the cold and miserableness that we're dealing with today.
Well, we're very glad you gave us our presentation, and anytime you're in town, when we can actually see people face to face, we'd love you to visit our observatory or one of our meetings.
You know me, if I'm in town, I will mysteriously find ways to drop by.
So Tamara, do we have anything else on our to-do list?
I'll stop sharing so you guys can.
I can't think of anything right now. I don't have any more announcements myself. Except thank you very much, Dr. Coiner. It was a great presentation. And I know I enjoyed it.
This is quite fun.
In lieu of additional announcements from you guys, I will shamelessly plug, we do at my college, we do have a physics and astronomy lecture series that we try to host somebody giving a talk every month. And this year, because of COVID considerations, all of those talks are virtual. And our next talk, which is in roughly 2 weeks, it's actually on November the 12th, is going to be a talk given by Dr. Tracy Becker from Southwest Research Institute, who works on the NASA Europa Clipper mission. So we're going to have a talk on November the 11th or November 12th. It'll be at 8:30 Tulsa time, talking about Europa Clipper and the search for habitability beyond Earth. So if you guys have a chance to watch that, I post links to everything we do. I have a Facebook page that's facebook.com/SOCC Physics. And you'll see all of the talks that we give that are virtual and all of the events that we're doing. And if they're virtual, we do have the link to the live stream so that you guys can chime in and you can watch the talk from the comfort of your own home and learn more about interesting things.
Cool, thank you.
I'm preparing the November newsletter this week, so if you could send me those links, I'll put in a plug for you.
I will gladly do that.
Greg, what is your Bartlesville Club doing next month?
Our next meeting is Monday. And well, we have elections for one thing. That's going to be kind of challenging. And then the speaker is going to be Ranger Nick from the, forgot his last name. Oh, good grief. Anyway, he's from Osage Hill State Park, and we're trying to set up a dark sky area there. So we're just kind of trying to figure out what we need to do and how to go about doing that. So it's that's pretty dark skies up there. I'm not sure what the Bortle range is, but it's really dark. So it's kind of be more businessy than presentation, I think.
Well, John Blazey's been going up there for some months now, talking to Nick and whatever. And apparently one of Nick's own goals as a park ranger is to get that place certified as dark sky site for the park. So that's interest already there. And so Blazey is talking to him about what we as a club can do to help him with all the documentation and stuff that has to be done in order to even apply for it.
Yeah, we've done things like brochures, and we're working on a sign for the park. This kind of spun out, if you got a minute, back in November, well, I guess New Year's Eve, we wanted to have a like a first light star party, and we were expecting maybe 10 to 12 people to show up there because it's like at 1 in the morning, and so we thought, well, I've got 3 telescopes, I think, and a couple camera kind of things set up out there. And we had 75 people show up. Unbelievable. I mean, it was just unbelievably number of people because, and so that kind of stimulated the interest in this. Actually, I think there's a video on Google. I'd have to go find it, or you'll have to search for it. Where a guy just set up a camera just kind of looking at the ground, but you can see the night sky in the background. And so anyway, that kind of stimulated this, and we're going to try to pursue it and see what we have to do. So it'd be Monday, the what, 2nd, I believe?
Yeah, Monday the 2nd. If any of you would like to attend, John Land is on the newsletter, and he's got the links already.
Yeah.
But if you send it to whoever, if anybody would like to, or I can send it, if anybody would like to attend.
Yeah. Warning, the first probably 20, 30 minutes are going to be boring because we got to do some businessy stuff. But any other questions on it? Is it Nick Connor? Is that his name? I think it is.
Yeah, it's Nick Connor. Nick Connor.
I don't know why that spaced out on me.
Brian, what's going on special at TASM? Anything for the holidays?
Yeah, actually, we're gonna do a Halloween event kind of thing this Saturday, kind of a trick or treat sort of themed thing, and we're gonna be showing a space themed episode of the original Scooby Doo before every show in the planetarium that day. So I'm looking forward to that. November, we've got our DC-3 and or C-47 coming in. Not sure the exact date on that. So we're supposed to talk about it in our next staff meeting. After that, don't know what we've got planned for the rest of the year just yet. We're kind of taking it kind of 1 month at a time right now.
Yeah.
But hopefully I hope we can get more World War II aircraft in, because the last weekend was the busiest week we've had all year.
Wow.
So I mean, every show I did was probably 80, 90 people in it, as up from like 30 on a normal COVID Saturday. So I kind of hope we can do that again.
Are you only open on Fridays and Saturdays?
Yeah, for the time being, just budget concerns, and it keeps everything easier as far as cleaning up for COVID and stuff like that. So stretches our supplies a lot further, but it's working out pretty well for us because we're seeing a lot more people on those days now than we did before. Just once we restricted things down, so it makes things a little easier.
Well, now that you're on the board, you can keep me posted and we can notify our members when something special is going on up there.
Exactly. I like that idea.
Well, Tamara, you still there?
Yeah.
I think everybody's kind of said their bit. Anybody else got something to say? So we should.
No, I'm just cold. I'm just trying to stay warm. I've only got a little, our central heat doesn't work anymore, so I'm having to rely on space heaters, and it is like just subarctic temperatures in here. So I'm just, that's all I can do.
Right. Well, I want to thank Dr. Corner for doing that.
Yes.
I get tickled calling him Dr. Corner.
Generally around here, it's still just Aaron, because everybody knows me.
Okay. Well, I like calling you Dr. Corner.
I understand. There are some people that like that, but I try to avoid using my title unless I absolutely have to. It's one of those odd things. The one thing I will ask, when I know this is being recorded, is there a chance that somebody could send me a copy of the recording, because I may put it with my archives of stuff that of presentations that I've given.
We'll put it both on the public and the private Facebook pages too.
All right.
We'll make sure someone sends you a link.
All right. I appreciate it. Thank you.
Yeah, YouTube works. That's what I normally do, is I just upload it to YouTube.
That's fine with me. I will go link it from my various websites when I.
Do you want the hard copy just so you can upload it to your own resource?
I'll just link it. I'll just link to your guys's. That way you can get some extra traffic that way.
Cool.
All righty.
Well, thank you, everyone.
Thank you,
James.
Thanks again.
Thank
Good
you.
seeing everybody.
Thank you.
Thank you.
Thank you.
Thank you.